So we are finally at the Lensmaker's equation. Lensmaker's equation is straightforward to understand and use, but it's a little tricky to derive. Most textbooks don't explain it very well, or don't explain it at all and just give you the equation, but I'm going to break it down for you myself here because I bothered to understand the derivation, and I think that you can too. So this is the game plan. So we're going to take a lens and consider each of its surfaces separately. Right? So the left curvature, radius of curvature in that surface separately from the right side surface and radius of curvature. Light's going to approach from the left and refract at the first surface and then form an image on the right. Then that image will serve as the object for the next refraction event, which is the right side of the lens. Right? So we're kind of deconstructing the lens and thinking of the lens as if it only had a left side, and then if it only had a right side. It's kind of non-physical for a bit. So, but here's the tricky part. This image object, right, this image is formed by light refracting at the left surface that forms an image on the right. It's still on the right side of the lens, but the light is still going to be approaching or incoming from the left side of the lens. So that's right. We're going to use light. We're used to light always emanating from the object, but here we'll have some scenario that I'll draw real quick where we are considering the right half of the lens, right, and the left half exists, but we're just not considering at this moment. And we are going to have some object that had been formed, right, some object that had been formed from the original image, which was over here, right, but we're going to be considering rays from this object, this arrow object here, but they're going to be coming in from this side. So how does that make any sense at all, right? How does that make sense? How could it be coming from the yellow arrow, but also coming from the left side? Well, it's a consequence of the weird sine rule. So our first sine rule said that if the object was on the same side as the approaching rays, the rays that are approaching the refracting surface, then the object distance is positive. And if you stop to consider this, you may have thought, well, when would that not be the case? If rays are always emanating from the object, when would it ever not be the case that rays are coming from the object and approaching or incoming on the same side of the refracting surface, right? Well, this is that case. And the way that it works is they approach from the left, but they approach in such a way that they would all intersect with the object on the right if there were no lens here. So all of the rays are incoming as if there was no lens there, they were coming from the tip of that arrow, if we're considering the top part of that arrow, right? So they're coming in this way, and you might be able to kind of make sense of this. They're incoming negatively, right? So they're leaving this object negatively, which would kind of mean that they're coming to the object, right? So instead of leaving the object negatively, we can say just as easily that they're coming toward the object from that left side. So that's the weirdness with this derivation. It's a little bit odd and unphysical for a bit here, but if we accept that, then we can arrive at a real answer in the end. So when the rays hit this refracting surface, instead of continuing on to the object, we are actually considering that there is a refracting surface, and they're going to refract as they otherwise would, something like this, and they're going to form a third image, like down here or wherever it is, right? And it's going to be image 2.0, right? So it's a two-step process here, and it takes a little bit of mind bending to figure out what's going on in that intermediate step, but we're going to walk through it. So that's the general game plan here of what's coming up with this. Of course, going to draw a better geometric picture. At this point, you know that geometric optics, they're not kidding. there is some geometry going on. So I said the game plan was to treat each refracting surface, the left surface and the right surface of a single lens separately, and by this I mean we will consider a two-part refraction event, where the first image is formed by the left surface and completely ignoring the right surface. And that becomes the super weird right side with left approaching rays object for the second refraction event at the right surface of the lens, completely ignoring the left surface. So I'm going to draw these independently to keep them straight, but first I'm going to draw both events happening on the same diagram here for you, because I want you to see what most textbooks give you and leave you with. I'll do it not as dramatically large like I did last time, so that you can appreciate the breakdown of what's going on here, because it took a sec for me to work back through this. Let's see, so it's going to be a little bit thicker. A little bit thicker. Then at the edges there. This is going to be NB, index of the material. This is going to be NC, and this is going to be NA. And it will become clear why that is. Even though this is the same material as that for most assumptions, since it's a two-part event, we gotta consider some weird index of refraction stuff happening as well. So we have an arrow, an extended object here, like that. This is going to be our Q, this is going to be our P. I'll even erase that dot there because we get it. And this is going to be our image distance here, right? And I'll do it to here. This is S. And we're going to have a couple rays. From the tip here, we're going to go straight across, and I'm going to draw it, well, the book drew it right at the center there, or right at that left edge there. So I'm going to draw that, just like they did. And then it's going to refract in such a way, I think we'll need a longer gray line there, like this. So it's coming out. All right. And then we are given that goes right through the center of curvature and arrives at, let's see, arrives at here, and back this guy up a little bit. There. This I'm going to do in orange as our intermediary image that's formed right there. That's Q prime. This is P prime, our first image. There's a radius of curvature going on. So actually, the center of curvature of lens 1 and 2 are irrelevant. So center of curvature of lens 1 is there, and center of curvature of lens 2 we'll say is there. And so this is the radius of curvature. Obviously not drawn perfectly, but close enough for us here. And this is for the second one, probably even farther off, but you get the point. All right. And so, like always, I should do all my gray stuff before. This is supposed to go through there. There we go. Orange, intermediate image, Q prime, P prime, there we go. And then there's a second event. I do blue. And this is what the book draws. Actually, I'm not going to do blue. I'm going to do a more vibrant color, like this guy? No, that was our mirror. This guy? Yeah. All right. So, coming out from this object, this is our image that was formed from the first part, but it's now going to be our object. So it's rays that are coming in from the left, approaching as if they were going to all arrive at the image here, right? So it's incoming negatively. Sorry, I'm going to write it. Incoming negatively, right? And then there's another one that is going to go, let's see, is going to, if we had, no, not do, line, so do, like that, and it's coming as if it would hit that, right? So that's supposed to be a straight line where it goes from solid to dotted. But what actually happens, we know, is it does refract at this point, and it makes it to down here. And we consider this guy, if it keeps going, I don't know how much room I'll need, keeps going. Let's say it refracts like that. Then it forms another image, which we'll use yellow because that's the final image. Down here, we'll call that Q double prime and P double prime. And so to clear it up, event 1 is white, and this cyan color is event 2. So that clears it all up, right? Very easy to understand. No, not really. So we're going to walk through this. But first, let me finish this guy up. So here we have, that works. We have the image distance from this first guy. There. Because there's a, right, this is corresponding to the left surface, this is corresponding to, or the right surface, and this is corresponding to the left surface, and there is some difference there, and we're going to call that difference T, and we're going to immediately ignore it because it's a thin lens. So we're going to say T is very small. Another way of saying that is T is much, much less than the object or the image distance, which we'll label here. All right, and I'm going to have to say this is event 1, and this is for the image for event 1, and this is now the object distance of event 2, so S2, and this then is the image distance of event 2, S2 prime. All right, so if you make 0 sense of that, or some but not all sense of that, then you're exactly where I was when I approached this derivation. But I unpacked it for myself, and I'm going to deliver it to you. So here's both events drawn separately, which makes much more sense, to me at least. So we have an optical axis again, straight across. We have event 1, right? That's what we're considering first. Event 1. We have a curved surface here. We're literally ignoring the right surface, so that's all that exists, which means, if you think about it, so on the left side, NA is air, but on the right side, NB is, we're going to say glass, right? Because that's typically what we're talking about, but it's the material of the lens all the way off into infinity. right? There's no end of the lens that we have to consider because we're literally ignoring the fact that that material has another surface on the right. So this is all the way to infinity, it's glass. And so for event 1, we're starting in the air, and then we're refracting at the air-glass interface, and we're ending in the glass, even though it's not physical, right? But we're just, theoretically, we're ignoring the fact that there's a surface on the right of this material. And so if we have an arrow here, that's our object, PQ, and we have a ray, just like we were doing before. One goes straight across. Now it's very obvious where it's refracting, and this is going to refract down somewhere, right? Somewhere. And we have our center of curvature, which is, I don't know where. Doesn't seem like it would be there, but just imagine I drew the lens differently, such that it is there, which means that this is going to be our radius, say R1, and we have another ray coming from the tip of the arrow that's going to go right through that center of curvature to here. All right, and we have an intersection point. I'll just leave them going too far, and I'll say that we have our intersection point here. So that's Q prime and P prime, right? All right, so, oops, let me do it orange to stay consistent with the other diagram. So orange, and since I've erased that already, let's just say the refraction isn't so wild, and that it meets there to give us just a little bit more room. There we go. Q prime, P prime. And this from here to there is our image distance, S1 prime. And our object distance in red is from that same point to here, right? Because we are considering for a thin lens. If it weren't a thin lens, then we would consider that thickness, but we're just saying that the thickness of the lens is nothing compared to the image and object distance. So we're considering right from, it doesn't necessarily have to be, there or, there, just somewhere that's the same reference, the same reference for each of those. There. All right, so now let's think about this for a little bit. Let's write things in gray. So we have a normal surface here and a normal surface here. Okay, so we have a angle of incidence we'll call alpha 1, and we have an angle of refraction, which we'll call beta 1. 1 because this is event 1. Okay, so law of refraction says NA sine theta A is equal to NB sine theta B. Thinking about this, theta alpha 1 and beta 1. There we go. Thinking about this, if we have, because this is air and glass, if we have NA greater than NB, then that means that as it enters the glass, the light slows down, which means that it bends more towards normal. Bends towards normal, right? So that means this angle is going to be bigger than that angle. So alpha 1 is bigger than beta 1. It's a wild beta. Beta 1. Okay, so keep that in mind. Make sure, if that doesn't make sense, those thoughts that we recently learned, so they're not as quick recall maybe. If you couldn't track through each of these thoughts, that fast. Pause the video and think through each one and make sure that all of those concepts connect for you. Make sure that all makes sense. It slows down, which means it bends towards the normal, which means that the angle of incidence is bigger than the angle of refraction. Okay, so now we have event 2. Event 2. Same deal. We have an optical axis, like that, and we have a surface, and originally I kind of drew it as a converging lens. It's still a converging lens because it's thicker in the center, but we're doing it kind of this way so that you have a convex surface if approaching from the left side for both cases. It's just the choice that we made. Let me do that a little better. Okay, something like that. Similar story where we have glass over here. Oh, well, actually, this is not similar story. So now, if we're considering this as our object for the second event, that means that we start in the glass, right? So everything on the left side here, we're now ignoring that there's a surface here. There is not, right? We're pretending there is not. And so that means that everything here off to infinity is glass. And that means that NC, air, right, it exits that second surface here, and it exits into air again. And so air is everything here off to infinity. Okay? So we have our object, which is this arrow that we left off with. Something like this guy, Q prime and P prime. And we have a center of curvature, which is somewhere here maybe, C2. And that gives us a radius of curvature that's something like that, which looks a little closer to reality than my other ones. And then we have this other color for event 2. So here's, once again, where it gets weird. So this is our object, but the rays are going to be approaching from the left side. But they're going to be approaching in such a way that they would all intersect with our object if there were no lens there. Right? Can you picture that? They're incoming negatively. So what that looks like is, I'm going to do this so that I can help my drawing. So we're going to have one going through the center of curvature, like this. And that one, the ray does not refract because it's going directly, it doesn't look like it, but this is a right angle, so it's going directly into it, and it doesn't refract. But the other one, so if we were to consider another ray, right from the tip here, up here a little bit, and I wish I gave myself more space with this stuff up here. Move. Then what happens is we want it to be approaching such that it would arrive there. So we're going to use this as a guide, but we know that it doesn't actually do this, right? The ray is physically there, but once it hits this surface here, it refracts and does some other business, right? So we're just using that as a guide to draw our line as it's approaching, but now we're going to back this up, right? Back this up. Hopefully that retained about the same angle there. And now we know that this, that this refract to a different spot, maybe here, right? So we're saying this, if it were to continue, would go all the way to the tip of that arrow, but instead it refracts. Okay, and maybe not so wildly, just a little bit. Okay, so dink dink. Actually, and so that means that this one, we're going to consider that it goes right on past there. And that's why I said not so wildly for this guy, because they do have to intersect. So let's just say it goes kind of like that, right? It doesn't matter how I draw it, once again, because we're going off of the actual laws, but you want your drawing to be somewhat close. All right, and then this forms the actual final image. So this is P double prime, and this is Q double prime. Okay, so we're going to go through the same analysis that we did in gray up here with law of refraction. So here we have the normal, which would be something like this, and we have the normal that would be something like this, right? I guess maybe what I should do instead, to be a little bit more convincing, heck yeah, let me back up all that, is to go from center of curvature, which isn't drawn perfectly, but at least it's close enough to give us a guide, like that. All right, so that means that this angle is going to be, we're going to call this B2, and this angle that it actually approaches at, not to the dotted one, but to the actual solid line, we're going to call gamma 2. I know I'm going kind of crazy with my notation, but I don't know, to me that makes most sense. So our law of refraction says NB sine beta 2 is equal to NC sine gamma 2. Okay. So because we have glass on the left and air on the right, we have NB being less than NC, which means that when it crosses that boundary, the light speeds up. Right? Make sure that makes sense to you, why it speeds up, what I mean by that. And then it also means that it bends away from normal. Bends away from the normal because it's speeding up. All right, and then that also means that B2 is less than gamma 2. Alrighty, so that should all make sense there. So now we understand the two refraction events that we're going to use, right? So this is separated. So this is all in one image, and then separated event 1 and event 2, right? So the hard part is really over, in my opinion. And to proceed, we are going to use the object image / radius of curvature relation for refraction at a spherical surface that we derived earlier. And we're just going to use it twice, one for each event, right? So we have two events going on. They're both spherical surfaces, refraction at spherical surfaces. And we have equations that we've previously derived, so we can just run through this now. So I'll go back to here before I run away with my view. So hopefully you had a chance to copy some of that down so you have the figures to reference for yourself. But we're going to say, well, I guess that's out the window, NA over S1 plus NB, I didn't, here we go. Let's do object and image distance here. So we have object, let's see, object distance. This is S2, and image distance These are supposed to be the same. S2 prime. All right. Since that's the notation that we're using, that way you can really reference what we're doing. So here we go. We have NA over S1 plus NB over S1 prime is equal to NB minus NA over R1. This is our object image radius of curvature index of refraction relation that we got, that we derived earlier and that we got from looking at just event 1. Right? Same thing, looking at just event 2 is NB over S2 plus NC over S2 prime is equal to NC minus NB over R2. All right. So taking in the medium on either side of the lens to be air, that means that we can say that NA is equal to NC, which is equal to 1, because that's the index of refraction for air. So taking that to be the case, and taking the index of refraction of the lens to be just n, just to simplify, then we have those equations becoming 1 over S1 plus n over S1 prime is equal to n minus 1 over R1. And likewise for event 2, n over S2 plus 1 over S2 prime is equal to 1 minus n over R2. Okay. Given that our sign rule tells us that S2 is equal to negative S1 prime, right? Let's think that through. Let's use this one since I think we can understand both events going on now. So S2, this image distance, that's positive because the image is on the same side as the outgoing rays from the refraction surface. But this S prime 2, let's see, no, S prime 1 is the image distance, and that is the one that's positive because it's on the same side. The image is on the same side as the outgoing rays. S2 is the object distance for event 2, and it is not on the same side as the incoming rays, and so therefore it is negative, right? It's negative. And so we have this relation that these are the same lengths, S prime 1 and S2, but opposite sign. And so let's come back down here, try this one more time. Hey, look, I was dead on. And let's carry on. So that means we have, so let's put that in parentheses, keep going. We have 1 over S1 plus n over S1 prime is equal to n minus 1 over R1. That one, nothing changes. But this one, the second one, is negative n over S1 plus 1 over S prime 2 equals 1 minus n over R2, right? I guess you can make either one negative if you want, right? So as long as they're opposite in sign. So I guess I went with the other one. So now we're going to add these two equations. So everything on the left gets added, and everything on the right gets added. So we have 1 over S1 plus n over S1 prime minus n over S1 plus 1 over S prime 2. All right, so then what happened here? This is supposed to be prime there, prime, and so that means that's prime there. Okay, so that means, no, what's happening here? What did I do wrong? Let's make sure and get this right, otherwise what are we doing it for, right? Yes, that's right. So we just traded in. We used this to plug in here, like that. And so that means that that made that negative. There we go. Okay, so it is supposed to be S1 prime. Okay, so then that means that these cancel out. That's what I was expecting. And we have on the right side the addition. So n minus 1 over r1 plus 1 minus n over r2. And as a quick aside, let's rearrange that to n minus 1 over r1 minus n minus 1 over r2, right? So that means we have 1 over s1 plus 1 over s prime 2 is equal to n minus 1, 1 over r1 plus 1 over r2. There we go. At this point, we've already kind of combined these two. We've added them two together. So we've taken the equation that we got from considering just the left interface and just the right interface. We've added them together. So essentially what we've done is we've started thinking of this lens as a single system again. And so we can go back to our traditional object image distance notation. So that means that S1 becomes S because that's just the object distance. And S prime 2 is the final image distance, right? So that can just be S prime. And we can say that again is equal to n minus 1 times 1 over r1 plus 1 over r2. And now we can recognize that the left side is very familiar. The left side is our thin lens equation, which is equal to, right, our thin lens equation, 1 over s prime equal to 1 over focal length. 1 over s plus 1 over s prime is equal to 1 over the focal length, and that is what this is, right? So we can say, flipping these directions, we can say n minus 1 times 1 over r1 plus 1 over r2 is equal to 1 over the focal length. Beautiful. We have arrived at what we wanted. We've arrived at an equation that involves the index of refraction of the material that you're choosing to use for your lens times the radius of curvature on the left side of the lens, radius of curvature on the right side of the lens, right? So between those two, you have the geometry of the lens, how to shape it, and then on the right, you have the focal length. So indubitably, you'd have the index of refraction of the material chosen by whatever material they're using, crown glass or whatever, and then you have a desired focal length that you're supposed to make this lens to, and so then you have the radius of curvature of the left and the right side there that is given by this equation. So this is the Lensmaker equation for thin lenses. All right. And so you just have to find a radius of curvature on the left and the right that satisfies those conditions. So this is incredibly useful because if you're designing a lens, it relates all the things that you need, and given a chosen material for the lens, you could just use this equation to determine the left and the right radius of curvature according to the focal length that you're trying to arrive at. All right, there you go.